the candidate list of things you want to find the median of, and then find some magic pivot, if you wish, in the middle, which we have this complicated procedure for finding. And then use that, find the rank of this element. So we have a special element here, let's call it X star, we find the rank of it. Right, which we can do by the linear scan, by scanning through the list and see how many things are below it. And then based on its rank, again, if R was less than n over 2, that means this number was below the median. That means we only want to keep things above the median. So keep everything above R, above X star, right? And if R is more than n over 2, keep everything below X star. So it's one of those things where rather than just doing the divide blindly and then working hard to conquer step, you're doing the divide very carefully and then going down only one of the two paths. And that was the whole point of median finding, that because we're only going down one of the two paths, maybe we'll get a much more efficient procedure than we've seen before. And I said that this will be correct as long as in this case, keep everything above X star and then invoke with, so let's say the select is the case select problem, right? And then we said set the pass k in. In this case, you pass k minus R. But just to adjust to the fact that you're looking for a different rank element in this case. Okay? And the argument I made last time was that this is a correct procedure because, in fact, the element you want, which is the kth smallest element, which is the kth smallest element, will be above the rth smallest element in this case. So we know it has to be in this set. So as long as we keep everything in this set and pass the same value, we'll be fine. Did I get this right? Or I got this one wrong. If R is less than K, no, see, I got it wrong. We got it right. Right, because now I've thrown away R elements and I have what's left. Its rank in what's left is going to be K minus R. Whereas on the other hand, if the rank of the element you picked is more than K, then what you're looking for is in everything below that, and its rank is going to stay the same because you're not taking anything out from below. So this procedure is correct. It will give you the correct answer. And if you had to now say, well, how long is it going to take to run this procedure, then again, there's the recurrence. And so let's say we're trying to find the median. So T of n is going to be some linear amount of work to do all this rank calculations and filtering, plus T of what? What is the size of the subroutine B? N minus R. Always. Where will it be n minus R? In which case? In this case. What about this case? Sorry? In which case? No. What is the size of the subset on which you run the recursion? It will be R. Right? So it's basically either n minus R or R, depending on which of the two things you pick. But that's no good. There's no way we can solve a recurrence like that because we don't know what's going to happen. We don't even know what R is. Right? So this is a problem, right? Because either it's Cn plus T of R or Cn plus T of n minus R, and we don't know what R could be. In the worst case scenario, what is the worst case scenario for these two situations? Sorry?
T of R. T of R, Cn plus T of R would be the worst case.
No. The worst case here would be we don't know what the value of R is. What is the worst case in terms of the value of R? N. That's great.
Oh, yeah. a 0 or 1.
That's great. So you're both right and wrong. You were correct that these are the two edge cases that cause us trouble. And depending on which of the two branches we're in, it's either good or bad. So this is a horrific mess. We can't analyze this at all. We have no idea what's happening. Which is why what we need intuitively is to say that no matter what we do, both of these numbers are small. We need to choose some magic value of x star so that the rank we get makes sure that whichever way we pick is small. In other words, we want to choose x. So this is the next goal. Choose x star such that the max value of r and n minus r is small. Because if that's the case, then no matter which way we have to go, because we don't know what's going to happen here, we're going to be fine. So we're trying to hedge our bets. We're like, I don't know what's going to happen. I want to look at the worst case scenario. And then where we always pick the worst case. And we want to make sure that in that case, it's number small. And what is small? Well, okay, I want it to be 1. That would be nice, but that's unlikely to happen. What would be acceptable? So this is another way of thinking about it. So if I reverse this around, okay, I don't know what this is. I know what I would like it to be, and then I can design my algorithm accordingly. So what would I like this to be? So now we can go back to the recurrence theorem and say, okay, if I have a recurrence that looks like T of n is equal to T of some n prime plus C of n, and I want this to be small, I want this overall running time to be linear, which is our goal. N log n is no good for us, right? Well, we can try various things. Suppose n prime is equal to n minus 1. We can hope to at least eliminate one thing every time. That's reasonable. What is the overall runtime we get? If we now call this recurrence T of n is equal to T of n minus 1 plus C of n, what are you going to get? Should be pretty straightforward. Just unwrap it in your head and see what's going to happen. You're going to get something like n squared, because it's going to be n plus n minus 1 plus n minus 2 plus. So that's not good. Clearly, you're not throwing out enough stuff. Okay. Suppose I put, I don't know, n minus 3. That seems to make progress. Does that help? No? You're just skeptical? It's not really going to help you. I mean, fine, you put n minus 3, but you still have, it'll be n over 3 times n or something like that. Right? You're just skipping 3 at a time. You still have n over some constant fraction of things. It's not going to help you very much here. So you need to do a lot better here. Suppose I could be really, really good. What is my ideal scenario, my dream scenario for this value? What should it be in this case? What is the best possible value of this I could get for any value r? N by 2 is the best possible. Right? There's no way you can get better than n over 2. Does n by 2 work? What do I get in that case? So this again, you have to think carefully, but if you think about it, this is very much like the recurrence for binary search, except this is an n. And if you work through it, by applying the Master theorem, so this is a 1 and this is a 2. So you basically get n to the log of 1 base 2, which is constant, and then versus linear, this is bigger, so this wins, and your answer is linear. So if we can actually choose r magically, so we always split in half, that would be great. But you don't need that. And that's the key thing. That's a lot. That's a lot to ask for. And you don't need it. Suppose this was, and I'm going to be a little silly here, relatively. Suppose I could throw out 1/100th of the input at every step. Would that be enough? You can again apply the Master theorem. Again, it will look like n to the log of 1 base 100 over 99, which is still a constant, because this is still 0. So this is going to be less than c times n, and you still get a linear answer. So again, looking at the recurrence tells you, I don't need to do too much, but I do need to be able to throw away a constant fraction of the input at every step. It doesn't have to be a big constant. It can be a tiny, I mean, I could make this 9,999 over 10,000. I mean, the constants would change, but the asymptotic worst case behavior would not. So obviously I want this to be I want to throw away as much as possible. But there's a gap between what we would like to and what is sufficient. And so the point here is that any constant here any constant I can put in is sufficient to get me what I want. Which makes my goal with R a little bit more tractable to say, look, all I need to ensure is that this number here is some constant fraction. Yeah.
This is the worst case we are saying equal in complexity, but on average case.
What does average mean? Average over what?
Obviously,
No. Average over what? If you're taking an average, you're averaging over something. What are you averaging?
average not. So worst case is like the worst example we get.
Yeah.
And average is then if we have all the possible spaces of inputs we have.
So you want to look at an average over all possible inputs. Or sum, what is the probability distribution of these inputs?
Yes.
No, you just said yes. I asked you a question. What is the probability distribution of the inputs? Are you assuming uniform distribution? It sounds like you were when you said take the average. So now you're saying, if I analyze the algorithm in the case where all inputs are equally likely, then on average this might look like this. That's perfectly fine. You can do that. Most of machine learning is based on those kinds of ideas, where you change the distribution. This is not a machine learning class. We want the worst case. We are very pessimistic. Think of yourself as a very, very suspicious person. You want to, and if you think of, for example, cryptography or security, you can't afford to do average case. Yeah. So everything we do here is worst case. When we do not worst case analysis, it will not be over the inputs. It will be over coin tosses of the algorithm. It will still be worst case, but the algorithm might make choices. You might compute averages over the algorithm's choices. We'll get to that in a month or 2 months.
Obviously, the fraction is less. Something this should be worse than the normal algorithm.
I don't know what normal means.
Normal means like if you are dividing into half,
Yeah.
then just divide it by like 100 or 1.
Oh, I didn't say it'll be the same performance. I said asymptotically it's the same. If I break them up into equivalence classes based on their asymptotic running time, the worst case running time in terms of n as a function of n, they'll be the same. The constants will change. Right? The constants will change here.
Yeah.
And there will be there's a homework problem around this that you will have to sort of explore. Yeah, the constants will change. Nothing comes for free, but a change in a constant is very different to a change in the actual dependence on n. Because as n increases, you want to see that. You had a question.
Could you just discuss again the n divided by 2? Like, yeah.
So what I was saying was that in the ideal case, when you always divide up perfectly, so no side was worse than the other, then this would be what your recurrence would always look like, right? And we could just unroll this, right? So this becomes, you can apply the Marshall theorem, or if you don't want to do that, you can say it'll be Cn plus C times n over 2 plus C times n over 4 plus C times n over 8. This is a geometrically decaying series, therefore the first term is the term that dominates. The answer is C times 2C times n.
And then, but that is not practical to always get. Is that?
I didn't say that. I said that's the ideal.
Right.
We would like to aspire to that, but we don't even need that.
Okay.
It is sufficient to have any constant. That's the best constant. But when you see things like n over 2, in many cases you should think, some constant. Right? When we do algorithm design at this level, you're not fixing, the 2 is not so important as the fact that it's constant. Right? The issue is really n over something versus n minus something. This is the big distinction where the change happens. That's what we care about. The value of C matters less, right? It will matter, but to get down from n squared doesn't matter. So, okay. This allows us now to go back to the first 3 steps of our procedure, if you recall, where we said break things into groups of 5. So we have these 5 elements. Take the median of each group, and take the medians of all of those. If you recall, I had argued that if you looked at the median of everything, so let's say this is the median, this is my x star, because this is the median of all the medians, and there are n over 5 of these, it is greater than or equal to n over 10 of them, half of them, because it's a median. Because each of those medians is greater than or equal to 2 more things, including itself, 3 more things total. This x star is more than 3 times n over 10 things. So its rank greater than or equal to 3n over 10. So why don't we sort of meditate on that for a second? Remember, the claim was, so step 1, x star is greater than or equal to n over 10 medians. Each median is greater than or equal to three numbers. Therefore, x star is greater than or equal to 3n over 10 numbers. Okay? Yes? Which means that we know that R is big. That means n over R is small. So, but that's not enough, right? Because if R is too big, then we're taking the max of these two things, and that will not be good for us. So not only do we need to say that the rank of x star is big, we need to say it's not too big, somewhere in the middle. And how do we say that? Exactly the same way. X star is less than or equal to n over 10 medians. Each median is less than or equal to 3 numbers. So x star is less than or equal to 3n over 10 numbers. Right? So now I have this fact, and I have this fact, which means I can now conclude that the rank of x star is greater than or equal to 3n over 10. The rank of x star is less than or equal to n minus 3n over 10, which is equal to 7n over 10. Yeah?
Just a quick comment since I'm sitting next to it. You're like right on the boundary of the.
That's the boundary? Thank you. Is that good?
You probably should stay on that third column and not make a fourth column.
So what I'm saying is I should even go here?
Probably not.
Okay. Okay. What about this side?
I think you're all good on that side.
Okay, good.
Yeah.
Thank you.
Yeah.
Good. So going back here, what can we say now? If we know those two facts, what can we say about this? We want a max. Well, we know that R is less than or equal to 3n over 10. Well, we know that R is, less than or equal to 7n over 10. We know that R is at least 3n over 10. So n over R is less than or equal to 7n over 10. So the max value is less than or equal to 7n over 10. And we have therefore achieved what we wanted. We now have the ability to say we are throwing away a 30% fraction of our input, no matter which way we go. And the cleverness is this idea that taking the median of medians has this nice problem. Another way to interpret what I just said is that the value x star I picked is an approximate median. An exact median, those would both be n over 2, 5n over 10. And like, not quite clear, but I got like a 3 and 7. Instead of 5 and 5, I got like a 3 and a 7. It's an approximate median. We will be talking about approximation algorithms later in the course, where these kinds of tricks will not be very useful. Because what I'm basically saying is very easily, I can find an approximate median. And for many problems, that might be sufficient. Because it roughly divides things off. Not exactly, but roughly. Yeah.
Maybe I missed it. The R, the rank, is that not 3n over 10? Or is it?
All we can say is that the rank is somewhere between 3n over 10 and 7 over 10. We don't know for anything we picked where it's going to be. So we don't have an exact handle on it. Because it could be anywhere, it's just the median of medians. But we know it's in this range, yeah.
So it will be same for any even or odd.
Yeah, pretty much. And again, the assignment will walk you through how to think about even odd as well. So that's a question. Question? All good? Okay. So now we are ready to wrap things up. So I'm going to go backwards here because hopefully this is the oldest stuff I wrote already written down. Again, I will transcribe all of this into a PDF note for you and put it up there, even though I didn't have my iPad today. So if you're scrambling to take notes, don't worry. I have both printed notes as well as what my right way are, so you can relax. You just take it out there. But I'm going to represent now, so don't panic if you solve it. Okay, let's wrap this up now. We had a recurrence that looked like, which I conveniently wrote out, but looked like T of n is equal to T of either T of max of R and n minus R in the worst case, right? Plus some constant times n for all the bookkeeping work we had to do to find the element of max of that rank and then throw out everything good. Right? Yes.
We need one more T of finding the medium.
We're not there yet, but very good. I'm going to get to it. Absolutely right. You're absolutely right. So now we can say, oh, this can be now written as T of 7n over 10 plus Cn. But as you pointed out, we're cheating because we haven't counted the time it takes to compute the median. Well, how long does it take to compute each individual median of 5? That is some constant. How many of those things are there? Well, there are n over 5 of those things. So there's one term for that, some C prime times n over 5. Okay? But there's also the median of medians. How are we computing that? We have those n over 5 things. We're computing their median. How are we doing that? Where did that answer come from? I see lips moving, but I'm not hearing you. Speak up. You want to say something?
Another constant term.
Another constant term. How do you solve that problem? Of, sorry?
One more constant term of 1 because you're taking median.
Well, I have n over 5 things, and I have to compute the median. Why would that take constant time? I have to solve the median problem on n over 5 things.
Can we
Recursively.
You have to recurse.